This is Math Studies, Lesson 9.4, Geometric Series. A geometric series would be adding the terms of a geometric sequence. So I think this one is a little complicated because we are adding up numbers that we got after we multiplied. But just like the arithmetic sequence versus series, in the geometric sequence versus series, a geometric sequence is just a list of numbers. A geometric series is add the numbers from that list of numbers. We have a way to add a couple numbers. That's called a partial sum. And if a series converges, that means it approaches 0. It has a finite infinite sum. That means you can add all the numbers in the series. But we got a formula in each case. So the partial sum formula is a longish formula. To add up a specific number of numbers, you need the first number from the list multiplied by the quantity of 1 minus the ratio to the power of n, divided by 1 minus the ratio again. So we should know what these are, but let's label anyway. U1 is the first number. R stands for ratio, which can be obtained by taking the second number and dividing the first number, or in a percent situation, 100% plus or minus the given percent, increase versus decrease. Same ratio right there. And n, I wonder if I can squeeze this in. N is number of terms. So if I wanted to add 5 numbers, power 5. If I wanted to add 10 numbers, power 10. An infinite sum is a much simpler formula. I don't remember how I represented this. Let me scroll down. Is it S or S infinity? I did S infinity. So the infinite sum would be if we want to add all the numbers in the list of numbers, only when a sequence converges. I'll say more to that in a second. We would take the first number divided by 1 minus the ratio. Since I have U1 and R labeled in the previous formula, I'm not going to label them now, but I'm going to talk about when this formula can be used. This formula only works decreasing geometric sequences. And so we'll have a quick talk about infinity. If a number gets bigger and bigger and bigger and bigger and bigger, it's never going to stop growing. So our arithmetic series, where we're adding a bigger number and a bigger number and a bigger number, the infinite sum doesn't exist because it's always going to get bigger and bigger and bigger. Same thing with the arithmetic decreasing sequences. They can get smaller and smaller and smaller into the negative, so we can go to negative infinity. For the geometric sequences, when they are increasing and getting bigger and bigger and bigger, it's never going to stop. But when they are decreasing, when we cut something in half, we can get a smaller piece and a smaller piece and a smaller piece until eventually the piece that we have left is so small that it is negligible and the series would stop growing. So that's a long way to say this only works for decreasing geometric sequences, only when your ratio is less than 1. If you have an arithmetic or an increasing sequence, then it will be automatically no solution. So some examples. We have a sequence 100, 800, 64, 51.2, and so on. I have us calculating the sum of 15 terms and then the sum of infinite terms. So the sum of 15 terms, we could do it the long way. We know we have the first and the second and the third and the fourth. We could figure out the ratio, find the 5th, 6th, 7th, all the way up to the 15th term. But we don't need to do all that. We only need 3 things to use my partial sum formula. We need the first number, we need the ratio, and we need the number of numbers. And 2 of these things are just given to us. We know that we're adding 15 numbers. We know n is 15. We know the first number in this list of numbers, that's 100. We don't know the ratio, but we can figure it out. We need to take the second number and divide it by the first number. 80 divided by 100, 0.8. So with the first and the ratio and the n, I can go right into my formula. I'm going to stack this up because I don't have too much space, but to calculate Sn, we need our first number times 1 minus our ratio to the power of n. And instead of divide, I'm going to go divide 1 minus the ratio. Plug and chug. 100. 1 minus 0.8. This power does have to be in the parentheses. Divided by 1 minus 0.8. Denominator also in parentheses to make sure our order of operations treats this appropriately. And if I added 100 plus 80 plus 64 plus 51 plus whatever's next plus whatever's next, so I have 15 numbers in the list, they would add up to 482.4, rounded. Now let's say I wanted the 16th and the 17th and the 18th and the 19th number forever and ever and ever and ever. So that's like I'm adding 100 plus 80 plus 64 plus 51 plus 41-ish plus 30-ish, and I'm going to add every single one of these numbers. My point is eventually these numbers are getting so small that I'm just adding 0. And when you add 0 to something, your sum is going to stop increasing. So if we're going to add all those numbers, we can use our infinite sum formula. I need the first number, and I need the ratio. And I had those over there, 100 for the first number, 0.8 for the ratio. Let's go into the formula. The infinite sum is first number divided by 1 minus the ratio. And I can actually do that one in my head because 1 minus 0.8 is 0.2, which is like 1/5, which is like 5 times 100, which is like 500. But in case we don't believe me, let's go 100 divided by, and we need our parentheses so that our calculator treats our order of operations correctly, 500. And you can see after 15 terms, we were already at 480. We were almost there. But add those extra terms, and we get up to 500 for our final sum. Example B, find the sum of the sequence. Similar situation. We have a list of numbers. If I want a partial sum, I want the first 10 numbers in this list of numbers added together. I need the first number, the ratio, and the number of numbers. I'm given my first number, and I'm told to add 10 numbers. The ratio to me is obvious. I see 2, 4, 8, 16. I know I'm doubling. If it's not super obvious, remember you can always take your second number and divide it by your first number to see that it is in fact multiplying by 2 as we move up the list. So the sum of 10 numbers would be the first times 1 minus the ratio to the power of 10 divided by 1 minus the ratio. And that is not what I wanted. 2. 1 minus power 10. Divided by 1 minus 2. That looks good. That would add up to 2,046. Now, if I wanted to add the next number and the next number and the next number and the next number, we should realize without even doing anything that if I'm adding all these numbers, 2, 4, 8, 16, 32, 64, 128, and 256, and the next, and the next, and the next, and the next, forever, this sum will never, ever, ever stop because the numbers are going to keep getting bigger and bigger and bigger and bigger. So without even doing a formula, I know the answer. But just in case we don't know it, let's do the formula anyway. We know the first number is 2. We know the ratio is 2. If I go into my infinite sum formula and I go 2 divided by 1 minus 2, 2 divided by 1 minus 2, I'm getting a negative answer. That doesn't make sense because I know 2 plus 4 is 6. Plus 8 is a bigger number. Plus 16 is a bigger number. Plus 32 is a bigger number. And it's going to get bigger and bigger and bigger. So if I get a negative sum, that should help clue me in, if I didn't figure it out already, that this answer is no solution. Our infinite sum only calculates with a decreasing sequence. 2, 4, 8, 16, 32, 64, and so on. That's increasing. No infinite sum. And we have example C. Jack baked a pie and promptly ate 1/2 of it. Determined to make the pie last, he then decided to eat only 1/2 of the pie that remained each day. Record the amount of pie eaten each day for the first 7 days. So I'm looking for a list of numbers. A list of numbers is much easier to generate recursively. So I'm going to put in my starting number. I know that I ate 1/2 of the pie on the first day. You know, I don't need to do this on the calculator. Let's just do this on the paper. Because we're going to do fractions. My calculator is going to give me decimals. Fractions are going to be much easier. So on the first day, he ate 1/2. And then the next day, he ate 1/2 of what was left. So if there's 1/2 of the pie left and you eat 1/2 of 1/2, you're eating 1/4. And so that means there is 1/4 of the pie left. So the next day, you're going to eat 1/2 of 1/4. You're going to eat 1/8. And then 1/2 of 1/8, you're going to eat 1/16. And then 1/32. So hopefully you can figure out that really I'm just doubling the denominator every time, which is why I think fractions are much easier than if I had gotten to 1/2 times 1/2 and I'm trying to write 0.00390625 over 1/128. So how much does he eat after 7 days? We can add these all together. Should we common denominator this or add up the fractions? I know the answer, but let's go fraction version just for fun. And we'll end up with a decimal, but that's okay because I want to talk about this in terms of percentages. Did I hit it? Yeah. So if you eat 1/2 of that, and then 1/2 of that, and then 1/2 of that, and then 1/2 of that, after 1 week, you've basically eaten 99.2% of this pie. So if we live forever, that hopefully is your cue that we're going to be doing a infinite sum. We'll take our starting number divided by 1 minus our ratio, and I'm going to decimal this. It's just a little less typing. We have 1/2 divided by 1 minus 1/2. We'll eat exactly 1 pie. Whew, that's it. Good luck on the exercises. Let me know if you have any questions.